Greetings and welcome to the video for problem set number 5 of Chemistry 223. And in this chapter, chapter 16, we're going to look at electrochemistry and how powerful it is and how there are so many implications for our day-to-day lives, i.e. batteries. But anyway, we'll talk more about that later. Anyway, like the other problem sets before, have the periodic table in front of you. mhchem.org/per tab is the one you should use. Make sure that you self-correct every problem on your problem set. The ones you get right, put some kind of self-correct symbol next to it so that I know that you know that it's right. And the ones that you miss, which is totally fine by the way, just self-correct them like heck. So put in the right answers, maybe make some notes how you do better next time. And that way when you turn it in, you will get full credit. So it won't have any problems. If you have questions on this material, talk to me, talk to the Avid/LSC Center located above the library on the main MHCC campus. Their website is mhcc.edu/avid. Free chemistry tutoring is definitely a good thing. They're cool people up there, and I do recommend it. So anyway, let's get into how this problem set will work. But first of all, you will need a handout. You'll need the table of redox potentials, which is found at the end of problem set number 5. Please use these values when doing the problem set. You will find other values online. They may or may not be more or less accurate. It's hard to say, but they will be different than the answers that I will present. So if you can use this table, that would be really cool. So use the table of redox potentials as well as a periodic table, and you should be good to go. Okay, let's get into the problem set. This is the first of our questions involving electrochemistry, and the first thing is to be able to balance a half reaction. And a half reaction is like a mini chemical reaction where electrons are showing. Usually chemists want to hide the electrons, but in this case we're going to try and show them. When you're balancing a half reaction, it makes a big difference if you're an acid or base. So just FYI on that. But it's pretty easy once you get used to these, and there's some examples online of how this process can be done. If you're in acid, you are welcome to add H plus and or water. So on the first one up there, H2C2O4, you can see that there's 2 H's on this side, but no H's on the other side. And also notice how there's 2 C's and only 1 C right there. So at the very least, we're going to have to add 2 carbon dioxides to make the carbons, and that way the oxygens work out. We're also going to have to add some H pluses to the product side. Now, in a balanced reaction like this, you have to make sure your charges are balanced. And because we're adding a couple of H pluses and H has a positive 1 charge, we're going to add some negative electrons to make them both balance out. So oxidation means electrons are on the product side. Reduction means electrons are on the reactant side. And again, it looks like on this one, the electrons will be on the product side, so this will be an oxidation. And then also remember that for acids, you can add H plus and water only, and in base, you can add hydroxide and water only. And you'll add electrons on both sides. So this first one then here's the balanced reaction. So again, we had to add 2 in order to make the carbons and the oxygens balance out. And then we also had to add 2 to an H plus because we have to add enough hydrogens to make those balance out. But by adding H plus, now we have some charge, all right? 2 H plus. And the only way to balance charge is to add negative electrons. So we'll add 2 negative electrons. And if you're ever uncertain on these kind of reactions, you can always go back and make sure that everything is balanced okay. So 2 H's on the left, 2 H's on the right, 2 carbons on the left and 2 carbons on the right, and 4 oxygens on the left and 2 times 2, 4 oxygens on the right. And finally, even the charges will balance. There literally is no charge on the reactant side, and the right side, product side, 2 times plus 1 plus 2 times negative 1 goes to 0. Everything is balanced for mass and charge. And again, because electrons are on the product side, this is an oxidation. Electrons are being lost. Now for the next one, nitrate going to nitrogen monoxide, all right, you've got 3 oxygens in nitrate and only 1 oxygen right there. So you're going to have to add 2 waters to the product side. You can only add for acid H plus and water. So we're going to add 2 waters to that side. But in the process then, you're going to have to add some H plus to the reactant side because water already has hydrogens and you need to balance them out. And if you start adding H plus, you need to add some electrons as well. So the next reaction, when it's all balanced out, nitrate again needs 2 extra oxygens, which water will deliver, but 2 waters give 4 additional hydrogens, so you have to add 4 H plus. And if you look at the charges, all right, nothing on the product side has a charge. Nitrate has a -1. We've got -3 from the electrons and +4 here. All the charges go to 0, so this one is balanced. This one now is a reduction. Electrons are on the reactant side. And finally, in base, you can only add hydroxide and water. And in the lecture, the video lectures that are available, or in the balancing redox reactions handout on the website, I have some ways that you can help you to balance things in base. It's not hard, but it's just a little funky at first. For this one, what you want to do is you want to end up adding 4 hydroxides first to the product side because, you've got to have some extra oxygen there. And when you play back and forth, then you're going to have 2 waters. And to balance the 4 hydroxides on the product side, where there's only 1 -1 right here, you're going to have 3 electrons. I recommend that you practice balancing base reactions just to make sure you're cool with it, and you'll be good to go for the stuff coming up. And that's a reduction as well, by the way. In this question, we're going to take 2 half reactions and balance them together in order to give the overall redox reaction. All of these are in acid, so that's important to remember. Remember, acid means you can add H plus and water. So on a question like A, what I would do is I would first start off by trying to balance the 2 species which are similar. And in 8A, tin and tin 2 plus look a lot alike, and H plus and H2 look a lot alike. So we'll balance those 2 out first. Then, before we combine them back together, we need to make sure that the electrons balance out. In a balanced reaction, you don't want to show your electrons. That's kind of seen as bad form in chemistry. And if all is said and done, we'll end up with a balanced reaction. So again, just to reiterate, you want to balance the half reactions in acid first, and then combine the 2 half reactions. One of them will be oxidation, and one of them will be reduction. And you want to combine them in a way that there are no electrons left, and I'll show you what I mean by that in a little bit. The first half reactions, tin going to tin 2 plus, and H plus going to H2. 1 tin on the left balances 1 tin on the right. That's no problem, but we do need to balance charge, and the reactant tin has no charge. The product tin has a +2, and you can only balance charge by adding electrons, so that 2 electrons go right there. And now this reaction is balanced for mass, 1 tin on both sides, and it's also balanced for charge. +2 minus 2 gives 0 on the product side, and that's what we have on the reactant side. The second half reaction, we do need to have 2 H pluses, and that's because hydrogen, the diatomic, has 2 hydrogens. We need to add that in. That means we're going to have 2 electrons right there. But if you look at this one now, it's balanced. Notice how the first one is an oxidation. Tin is losing electrons. But the second one, the hydrogen ions are gaining electrons. The second one is a reduction. And on these, you always want to have one species being oxidized and one species is being reduced. So now that you have the 2 balanced half reactions, you just want to combine them in a way that all the electrons cancel out. And you can see there that the 2 electrons on the reactant side of the second equation are canceled by the 2 electrons on the product side. So the overall balanced reaction, tin plus 2H plus, goes to SN2 plus H2 gas. And you can always double check your final answer. Make sure that they're balanced for mass. So a 10 on each side, check. 2 hydrogens on each side, check. So balance for mass. They'll also be balanced for charge. So on the reactant side, 10 doesn't have a charge, but the H plus times 2 would give positive 2 overall. And on the product side, the H2 doesn't have a charge, but 10 has a positive 2. So those two are balanced for charge as well. So that reaction is good to go. Now for the second one, dichromate is Cr2O7 minus. And notice there how dichromate has a 2 by it, and chromium plus 3 is just 1. So when we balance the chromiums out, we're going to have to add a 2 to the chromium. The irons you don't have to balance out for mass, because 1 iron on the left, 1 iron on the right. That's no big deal. So let's start breaking them up. When you add the 2 for the chromium plus 3, lots of things start happening. First of all, dichromate has 7 oxygens, so that means we're going to have 7 waters. Remember, in acid you can only have H plus and water. And by doing that, 7 times 2 for the waters, that's 14 hydrogens we have to add to the reactant side. So now this reaction is balanced for mass. However, 14 times H plus would be positive 14 minus 2. That would be positive 12 in the dichromate and the positive 14. And on the product side, you have 2 times positive 3, positive 6. So in order to make the left-hand side's positive 12, like the right side's positive 6, you need to add 6 negative electrons. So this reaction is a reduction. Dichromate is being reduced to chromium plus 3. Now the second reaction, all right, we need to add an electron to the product side, because positive 3 iron minus 1 would give you the positive 2, and that makes this reaction balanced for charge. But notice here that there's also a 6. Initially, the iron to iron plus 2 to iron plus 3, that's just a 1 electron transfer. And when we combine the iron with the earlier dichromate, we need to cancel out all the electrons. And dichromate has 6 electrons. So we're going to multiply that second reaction through by 6. We're going to have 6 iron plus 2s going to 6 iron plus 3s plus 6 electrons. And then the electrons on the product side of the iron reaction will cancel the 6 electrons on the reactant side for the dichromate. So combining these two together, the electrons cancel out. You're left with dichromate and 14 H plus and 6 iron plus 2s going to 2 chromium 3 pluses plus 7 waters plus 6 iron plus 3s. Whew. And again, if you get to this point and you're not feeling confident, go through and balance, and you'll find that on this reaction, all the atoms on the reactant side are equal to the atoms on the product side, and also the charges on the reactant side will equal the charges on the product side. For this reaction, we're going to do the same thing we did in the last problem, where we balanced 2 half reactions and combined them to cancel electrons. But for this one, we're going to do it in base. And in base, you can only add, at the end of the day, hydroxide and water. So it's very similar to last time. We'll break them up into the half reactions, make sure everything is canceled out, stuff like that. You should still have one side being oxidized, one side being reduced, so that when you combine them, the electrons cancel. If you don't see that, double check your work. But anyway, for the first one then, pretty chill. You can see here, like the nickel 4 oxide compound has 2 oxygens, and there's 2 oxygens right there. However, there's no hydrogens initially on the reactant side, and the hydroxide has that. It's weird playing with water and hydroxide initially, but to make this balance out, if you add 2 waters to the reactant reactant side and 2 hydroxides to the product side, you're going to be good to go, and all the atoms will cancel out. In the lecture notes, I talked about an alternative way to balance these, where you add H plus and water first, and then you go back and neutralize in base. And I would probably find that easier. But on the other hand, if you're cool seeing these kind of things, you can do it. You want to add water to the hydrogen deficient side, and you want to add hydroxide to the oxygen deficient side. Anyway, the second one is easier. All right, you've got zinc on the left and zinc 2 hydroxide on the right. So that one, we just need to add 2 hydroxides. And to make the charges balance out, we're going to add 2 electrons. And double checking, the first reaction is reduction. Electrons are being added to the NiO2. And the second one is an oxidation. The zinc is losing 2 electrons. So let's combine them now, make one big equation, make sure those electrons cancel out, and at the end of the day, NiO2 plus 2 waters plus zinc makes NiO2 plus ZnOH2. And again, you can always check yourself at the end for charge and mass. This balanced reaction has no charges at all, so that's easy, and you should be able to see the mass atoms are the same on both sides. So the next one, same kind of thing. Break the irons apart from the chromium compounds. All right. Again, on the first one, the iron 2 hydroxide on the left, the iron 3 hydroxide, we're going to add 1 hydroxide to the reactant to make that side balance. But because hydroxide has a -1, we're going to add 1 electron to the product side. That thing is now balanced. Now the next one's a little funkier. We've got chromate now, and chromate is going to this CrOH4 -1 complex ion. The reactant side is certainly hydrogen deficient, so start by adding water to the reactant side and then add usually an equal number of hydroxides to the other side. Yeah, so then you can go back and make sure that balancing of charges is okay. On the product side, 4 hydroxides, that's -4, and an additional -1 from the complex ion. So the product side is -5. And chromate on the reactant side is the only thing with a charge at -2. So we need to add 3 negative electrons to make sure that thing is balanced for charge. Finally, when you combine these two, we need to multiply the first reaction by 3 in order to make the electrons cancel. Again, you want to make sure all the electrons cancel. Don't show electrons in those final balanced reactions. And if you do that, this is what you end up with: 3 FeOH2s and chromate and 4 waters. And that makes 3 FeOH3s plus the complex ion CrOH4- plus a hydroxide. And notice here how there were 3 hydroxides on the reactant side and 4 hydroxides on the product sides. So almost all of them cancel, but you still do end up with 1 right there. So this is the final balanced reaction in base. And again, feel free to go back and check it for mass and charge to make sure we're good to go. This is a question that shows a type of nomenclature used for electrolytic cells. And you can see there's lines and double lines and stuff like that. We'll talk about that in a minute. A voltaic cell, which is also called a galvanic cell sometimes, is a cell that is spontaneous. So that means that it would have a delta G, which is negative. We'll talk about that later. But more importantly, voltaic and galvanic cells are just electrolytic cells where you put them together and something happens. And believe it or not, there is sometimes utility of putting a cell together and nothing happens, and we'll talk about those later. But anyway, if you hear voltaic or galvanic, that just means that something's going to happen when you put all this stuff together. So if you look at this up here, it's going silver to silver plus, all right? And silver to silver plus, you can see that there's an electron missing when you jump over that first line. So this side on the left This side is the source of oxidation. Silver is being oxidized to silver plus 1. And if something is being oxidized, it's called the anode. So in an electrolytic cell, the anode is the source of electrons. And electrons will be on the left side, on the side where the oxidation is happening. Now, the electrolytic cells have a salt bridge and wires in between them, and the double line there just says, hey, I'm separating the anode, sources of oxidation of electrons, from the cathode, which is the places the electrons are going to be. So in this problem, the anode is on the left, the oxidation, and the cathode, which is the site of reduction, is going to be on the right. And sure enough, you can see here that chlorine is neutral, and it's going to chloride, which has a -1 charge. So chlorine is gaining electrons. It's becoming chloride. Now, there's lots of symbols up here. S means it's a solid, so it's solid silver. AQ, of course, means it's based in water. The chlorine here, the chlorine is a gas at a pressure of 1 atmosphere, which is important, we'll see later. And it's turning into chloride, which is also based in water, at 1 mole per liter. And this thing on the far right, platinum, you need a way to get the electrons into the chlorine to make chloride. And platinum is the avenue, if you will, that's being conducted through. Platinum is usually pretty inert, so it's a good way to transfer electrons from the anode to the cathode. So if you see this kind of nomenclature, just realize your electrons are moving left to right. They're going from the anode on the left to the cathode on the right. And anode means it's oxidation, losing electrons. Cathode means it's gaining electrons. So we can now start putting this stuff together. Let's do the equations for the oxidation, the anode on the left-hand side, and reduction, the cathode, the piece on the right-hand side, and then figure out what it looks like overall. No problem. So silver's going to silver plus. It's losing an electron. We're going to combine it here in a little bit. That's what those 2's are for. We multiply it by 2 because chlorine is a diatomic, and we have to have 2 chlorides on the other side, and that's going to require 2 electrons. So you can see the electrons cancel, and then overall 2 silvers and chlorine makes 2 silver ions and 2 chloride ions. Now, we talked earlier about this. All of these diagrams for voltaic galvanic cells, electrons move left to right. So the anode, which is where the oxidation occurs, is going to be on the left. That's where the electrons are coming from. And the cathode is going to be the chlorine going to chloride. The cathode is the right-hand side. That's where the electrons are going to. So electrons are coming from the anode to the cathode. They're jumping over the double lines, if that helps you. It kind of helps me for some reason. I don't know. But anyway. The last part here, you can have lots of different answers here, but just hopefully you're seeing the big idea. It says electrons in the external circuit flow from the, and you could say anode to cathode. You could say from the silver to the chlorine. You could say from the oxidation to the side of reduction. And any of these kind of things are totally fine. A lot of times voltaic cells have a little charge symbol, negative or positive. The anode is the negative cell and the cathode is the positive cell. So you could put that down too. You have to have negative ions moving around as well. The negative ions are going to move in the opposite direction. So they would go from the cathode to the anode or the chlorine to the silver. That's not as important as the other parts, but hopefully you're seeing what this kind of nomenclature means, and you can interpret it then for different kinds of cells. For this reaction, what we're going to do first is we're going to balance the 2 half reactions. All right, we're going to figure out what the overall reaction is, and then we're going to use the standard reduction potentials, the E0 values, to figure out out if the reaction is product favored or if it's reactant favored. So you're going to need those standard redox potentials handout that we talked about at the very, very beginning of this video to do this. And there's two examples, and we'll do one on this page and one on the next page. So the first one, we've got iron plus 2 and copper 2 plus going to copper and iron plus 3. And again, like we've done already before, I won't go through it as thoroughly as I have before. You need to balance them for charge, which means add electrons. So the iron plus 3 needs 1 electron to make 3 minus 1, make it the positive 2. Copper 2 plus 2 negative electrons gives neutral copper, so that's good. Multiply the first reaction by 2 to make sure the electrons balance out. And you've got 2 iron plus 2 and copper 2 plus going to 2 iron plus 3s and copper metal. All right, no problem. Now, this is what we've done before. But the new part now is that we want to try and find half reactions that look like R2 half reactions. And you can combine the cell potentials, which are these E naught things. E means cell potential, and the little naught means standard conditions. We're going to combine those cell potentials to give the cell potential of the whole cell. And the value of E will tell us if the reaction is spontaneous or not. So if you look at that table of redoxes, and I definitely recommend you check it out, the second one, the copper plus 2 electrons in copper, that will be listed right in there because they are tables of reductions. They're reduction potentials, all right? They're all listed by redox. But the second one here with iron plus 2 going to iron plus 3, that one won't be in there explicitly because iron plus 2 going to iron plus 3 is an oxidation, all right? So in your mind, you have to translate an oxidation into a reduction, and it's pretty chill. If you need to reverse oxidation, so instead of being iron plus 2 going to iron plus 3 plus an electron, think about it as iron plus 3 plus an electron going to iron plus 2. That would be a reduction, all right? And you will find that in there. But in our problem, we want it as the oxidation, not as the reduction. And there's something you have to do to figure that out. So if you look in that table, all right, you will definitely find copper 2 plus and 2 electrons going to copper, and it's got a positive 0.337 volt number associated with it, and that's cool. But you don't see iron plus 2 going to iron plus 3, but you see iron plus 3 going to iron plus 2, and that's got a positive 0.771 volt value to it. We don't want this in this version. We don't want a reduction. We want an oxidation, all right? So what we need to do is we need to flip that half reaction around, and no problem. If you flip it around, all right, and you turn that into iron plus 2 going to iron plus 3 plus an electron, you flip the sign of E. So what was a positive 0.771 volts becomes a negative 0.771 volts, and that's what we want in this problem. And once you flip it, then you can just add these two cell potentials together to get negative 0.434 volts. So I want to talk about that one more time, all right? We wanted an oxidation, but the table that which is very common, by the way, the table that was given was a table of reductions. So you look for the reduction version and you flip it, which is what we did down here at the end. And when you flip it, change the sign. So what was positive becomes negative and negative becomes positive. Now, our cell potential is negative 0.434 volts, and negative E cell values are not product favorite. And I like to use the idea that you've probably heard about 9-volt batteries or the AA's and stuff, which are, I think, 1.5 volts or something like that. They're not negative numbers, all right? And if you put an old battery in and it's been used a lot, nothing is going to happen. A negative cell potential means you try to put this, make it a battery, and nothing's going to happen. So if you calculate negative E cell values, those are not product favored. They would be reactant favored, but more importantly, that's like a dead battery, and those are kind of lame. Well, if you want to, play with your Xbox controller and you need a battery, then of course the negative E cell battery wouldn't help you very much. You want a positive one, right? So negative E cells are not the ones that are going to happen. You have to do something else, and we'll talk about that later. But for right now, you see how to calculate these E cells, and you're looking for positive numbers if you want the reaction to occur. Now, sometimes in books they'll talk about E cathode minus E anode, and that's fine too if this is a way that works for you. And what it's referring to is that if you go back to the redox tables, all right, which are these things right here I just circled, the cathode, the reduction, all right, that's the copper 2+. That's the one we wanted to be reduced, all right, but we wanted the anode to be an oxidation, obviously not a reduction. So 0.337 minus 0.771 is an alternative way to get to negative 0.434. I find that kind of confusing, and that's why I prefer the system I told you about, which is where you flip the reduction to the oxidation for the one you want, and you change the sign and add them together. But they are the same thing, and if that way works better for you, that's cool. Now, the second reaction is similar. It's permanganate and Mn2+, and nitrogen monoxide and nitrate. And the first thing, like before, you've got to balance this out. Now, this is a lot more involved of a reaction to balance, but it's the same kind of thing. All right, you start off with the manganese 2+ and the permanganate. Permanganate has 4 oxygens, so you need 4 waters, and that means you need 8 H+. And when you figure out the charge, reactant side has -1 for permanganate and +8 for the hydrogen, so that's +7, and manganese +2 is +2, so you need to add 5 negative electrons to make that happen. Second reaction, nitrogen monoxide and nitrate. Nitrate has 3 oxygens, so you're going to need... I need 3 oxygens, duh, but there's an oxygen already there. Sorry, instructor spaz, it happens. So you want to add 2 waters to make the oxygens balance. Sorry about that. That means 4 H+ on that side to make the mass balance. Nothing on the reactant side has a charge on this one, but you've got -1 for nitrate and +4 for hydrogens, so you need -3 electrons. So the parts in brackets are the balanced half reactions, and again, when you combine these, you've got to make those electrons cancel. So 5 and 3, common denominator of 15, if you will. We need to multiply the first reaction by 3, because that'll give us then a total of 15 electrons, and we'll multiply the second reaction by 5 to have 15 electrons on the product side. So when all is said and done, this is the half reaction you're going to get out, and it's all stuff you can do. It's great practice, and I encourage you to check it out while you're doing it. That's balancing the reaction. Now, like before, we're going to try and figure out the 2 half reactions from tables of reductions. And if you look on the redox tables, these are the 2 you're going to see. You're going to see a permanganate one as is. All right, permanganate plus 8 H+, etc., goes to 4 water, positive 1.51 volts. But you won't see the second one because that's an oxidation, but you will see the reduction version. So nitrate plus 4H plus 3 electrons going to NO, etc., positive 0.96 volts. And then like before, we need to flip the nitrate around because we don't want it as a reduction, we want it as an oxidation. If you do that, change the sign, all right? So the positive 0.97 becomes negative 0.96 volts. Add that to 1.51 and voila, positive 0.55 volts. So this E cell is a positive number, and positive E cells, product favored, all right? This is the battery. You put it together, it's going to work, all right? And usually that's what people want, but sometimes it's cool, as we'll see, to have negative ones too. But on this one, definitely you're going to get a positive E cell value. Like before, if you want, you can go cathode minus anode, all right? So the cathode, where we want the reduction to happen, the permanganate is 1.51, and the anode, where we want the oxidation to happen, would flip this one. I don't like that as well, but it is something that people find helpful sometimes, and you're welcome to use it. Just don't get them mixed up and stuff. Also notice that we multiplied these half reactions by 3 and 5, but we didn't do anything like that down here. Like we didn't take minus 0.96 and multiply it by 5, and we didn't take 1.51 and multiply it by 3. These numbers, the 3s and the 5s, don't affect E cells, and that's important. So just leave those for balancing, but don't apply them to the E cell values. In this problem, we're going to look at the value of having a good table of redox values. And a good table of redox values, in my opinion, has the E naught values listed from most positive to most negative. And you can see with this partial table there on the right, that's what we have. So copper 2 plus going to copper is positive 0.34 volts, aluminum 3 plus going to aluminum minus 1.66, etc., etc. This is a table of reductions. You can see that electrons are reactants. So the reactant is gaining electrons to become a reduced species. So if you have a table like this, which is by far the most common, there's some kind of neat things that you can do with it. And these questions will help to exemplify the things that can be done with a good table. So the first one says, based on these E naught values, which metal is most easily oxidized? Now, when it comes to those E naught values, the more positive value, the more easily things will happen, the more powerful it is. And so at first it might be tempting to say, oh yeah, copper 2 plus, because it's got the most positive value, positive 0.34 volts. But I didn't say which metal is most easily reduced. Copper 2 plus is most easily reduced to copper because it has the most positive value. And indeed, oxidation is the opposite of reduction. So if you have a table of reductions like what we have here, and there's a question about oxidation, you need to flip all of those reactions around. So instead of aluminum 3 plus and 3 electrons becoming aluminum, you would write aluminum solid becoming aluminum 3 plus and plus 3 electrons. So we need to flip these reactions around to make them oxidations, because right now they're reductions. And when you flip something around, the sign of E naught changes. So negative values become positive and positive values become negative. So what we want on this question is we want the most positive oxidation number possible. That's going to be the metal which is most easily oxidized. And if you flip all of those around, you can see that aluminum will be most easily oxidized, because what was a minus 1.66 volts will become a positive 1.66 volts. So aluminum will lose 3 electrons to become aluminum 3 plus. That's aluminum being oxidized. And the most positive value there, positive 1.66 volts. Copper going to copper 2 plus would be the least easily oxidized. It's going to have a negative value, so it's not going to be very easy to do that at all. On the other hand, aluminum going to aluminum 3 plus, no problem. Now the next question says, which metals on this list are capable of reducing iron 2 plus to iron? So if iron 2 plus gains 2 electrons, it'll make iron metal. And you can see in the table right now that that reaction has a value of minus 0.44 volts. So we need a metal which, when it's being oxidized, not reduced, which is what the tables are right now, but oxidized, it'll have an E naught value larger than 0.44 volts. All right, we need something that's going to be able to overpower that. So if you think about the last problem, if you would flip the zinc and the aluminum reactions around, so zinc would make zinc 2 plus and 2 electrons, and aluminum would make aluminum 3 plus and 3 electrons, you're going to have then positive 0.76 volts for the zinc and positive 1.66 volts for the aluminum. So that when you combine those oxidations now, not reductions as listed, but oxidations with the iron reaction, you're going going to get an overall positive E naught value. So both zinc and aluminum will be capable of taking iron 2 plus to iron. Let's show an example of how that would work with the zinc. If I flip the zinc reaction around, I would have zinc going to zinc 2 plus 2 electrons, and that would be positive 0.76 volts. And we want to make iron 2 plus add 2 electrons go to iron, which is minus 0.44 volts. So you can see then when I add those together, 6 minus 4 would be 2, 7 minus 4 would be 3. It looks like it's going to have an overall value of positive 0.32 volts. And because that value, that overall value is positive, that means that zinc can convert iron 2 plus into iron. If we would have done this and we would have ended up with a negative 0.32 volt value, then it would have been something that couldn't have happened. So both zinc and aluminum are capable of turning iron 2 plus into iron, but it wouldn't work for tin and it wouldn't work for copper, because if we would flip those reactions around, we would end up with an overall negative E cell value. So again, looking for positive E cell values is kind of the punchline on a lot of these problems. For C, it says write a balanced chemical equation for the reaction of iron 2 plus with tin. Okay, so the iron 2 plus reaction is already in the table there. And so we would have Fe2 plus 2 electrons making iron. So we have the iron 2 plus, that's a reactant, and we want to have tin metal as a reactant as well. So what we're going to do is we're going to flip this reaction around. We're going to flip this reaction so that we have tin now on the reactant side, and that's going to make tin 2 plus and 2 electrons as products. So we're going to flip it around. If you combine these, you can see how the electrons will cancel, which is good. We don't want to show any electrons. So the balanced reaction then will be iron 2 plus and tin metal, making iron metal plus tin 2 plus metal. So that will be the overall balanced reaction. Now, when it says about product favored, reactant favored, we need to go back to those E naught values. So the iron 2 plus going to iron, minus 0.44 volts. And we flip the tin reaction around, so minus 0.14 volts will become positive 0.14 volts. So if you combine these together, then you're going to get minus 0.30 volts. So minus 0.44 plus positive 0.14 will be minus 0.30 volts. And it's the magnitude of this overall E value which tells you if it's product favored or reactant favored. Negative overall E cell values are reactant favored. So this reaction is not going to occur very readily. All right, it's going to be more reactant favored. Iron 2 plus and tin will probably not make a lot of iron and tin 2 plus. Now, that being said, if you flip the whole answer around and see, so iron plus SN2 plus making iron 2 plus and tin, then you'd have a positive 0.30 volts. And that reaction would likely happen. That would be product favored because it would have a value of E which was positive. So again, look to the signs here to see what the values will be. And if it's a positive overall E, it'll be product favored. And if it's a negative overall E like this one, it'll be reactant favored. Now for D, we're going to do the same thing like we did on the last one. You want to have zinc 2 plus and tin metal as reactants. So we're going to have zinc 2 plus and 2 electrons making zinc metal, minus 0.76 volts. But we want to flip the second reaction around because we don't want tin metal as a product, we want tin metal as a reactant. So we're going to flip this one around. Tin is going to go to tin 2 plus 2 electrons. We're going to flip that one around. It'll be positive 0.14 volts. So when you add these reactions together, the electrons will cancel. You'll have zinc 2 plus and tin metal. making zinc metal plus tin 2 plus. That'll be the overall reaction. And then to figure out the product favored, reactant favored, we're going to take minus 0.76 volts and add it to positive 0.14 volts. And that comes out to be minus 0.62 volts, which is a negative number, and it's reactant favored. So this one as well has a negative E cell value. It's going to be reactant favored. Product favored reactions will have positive E cell values. So hopefully you can see from this problem that you can use a table like this to tell which reactions will occur, i.e. positive E values, which are product favored. You can also use this table to find out which reactions are less likely to occur, i.e. negative E cell values, which are reactant favored. So a lot of cool things you can glean if you understand how these tables work. And again, positive values are the ones that will occur more readily. This question says, calculate the cell potential, the E naught or whatever, at 298 Kelvin, developed in a voltaic cell using the following reactions, but notice that all dissolved species are 0.015 moles per liter, all right? So here is the balanced reaction, and it's saying calculate the voltaic cell potential. Okay, no problem. So what we would do normally on a problem like this is we'd break it into two half reactions, and you should probably do that here too. However, because everything is at a weird concentration, we can't really use just E naughts here. The E naught cell, like this thing right here, that means standard conditions. So that means 298 Kelvin, but it also means 1 mole per liter for dissolved species. And this species are not apparently at 1 molar. So if you have these non-standard conditions, either for temperature or like in this case for concentrations, that's where this thing is going to come in, and it's called the Nernst equation. And the Nernst equation is pretty helpful because most things are not at 1 mole per liter, or they're not at 298 Kelvin. So this Nernst equation will be helpful. The first part of this problem is just like before. We're going to balance it, all right, and figure out what the cell potential is. And the number we're going to calculate is this E naught. All those cell potential values, tables of reduction, are E naught values. They're standard condition values. So we'll figure out what E cell is, and we'll use that in the Nernst equation. So like before, balancing the half reactions, iron plus 2 going to iron plus 3, you have to add an electron. Hydrogen peroxide going to water, we'll add a 2 right there, add some hydrogens, add 2 electrons. Notice we've got one thing being oxidized, one thing being reduced. I flipped this reaction, the first reaction, around, turning it to negative 0.771 volts. You would see it in the table of reduction as iron plus 3 plus an electron going to iron plus 2 is positive 0.771 volts, but we want it as an oxidation, not a reduction. So add them together, you end up with 1.00 volts, good to go. And this is the overall reaction. Now, this is what we've done before. This number is the E naught, all right? That's the standard condition. And what we need to do now is apply the Nernst equation. And the Nernst equation is used, again, when your solutions aren't 1 mole per liter, when you have temperatures other than 298 Kelvin. If you have a gas, then the pressures are not 1 atmosphere, stuff like that. This thing right here is the Nernst equation. E equals E naught minus, parentheses, RT over NF, natural log of Q. All right? Now, let's go through these. E naught is the number we just calculated. It's the 1 volt standard cell potential. R is 8.3145, and that's a number, I called it the energy R earlier, and you can do it. T is the Kelvin temperature. Kelvin temperature is 298, so that's not a problem. N is the number of electrons transferred. And if you go back to the half reaction, 2 electrons are here, and 2 times 1, 2 electrons are there. So N is going to be 2, and you can see that's the number that I placed in there. Now, F is a constant. We haven't seen this one yet. It's called the Faraday constant. The number of F, it's 96,485. That's the value of F, and it's in coulombs per mole of electrons. And we'll see this in another problem here coming up. in this problem, if temperature is 298, RT over F are all just constants, and it comes out to be 0.0257. So to save some room, if you will, I just use this version. But you could also go R, 8.3145 times T, 298 Kelvin, divided by F, 96,045, and you should get that 0.0257. Now, the last part of Nernst is Q, and that's the reaction quotient we saw from the equilibrium chapter. And quotients, reaction quotients, are always products over reactants, just like all the equilibrium constants we've seen so far. So, if you go back to our balanced reaction up here, you don't include solids and liquids, so we don't have to worry about the waters. All right, that's out of here. But you do have iron plus 3, and there's 2 of them. And you've got iron plus 2, and there's 2 of them. So you can see that's where that comes from. There's only one H2O2, but there's 2 H pluses, so we'll do that there. And in this problem, all the dissolved species apparently are 0.015. So you can see there's lots of 0.015s in this reaction quotient, no problem. And of course, if you want to make it easier on yourself, those would cancel. It would be like natural log 1 over 0.015 to the 3rd power. This is just fun for your calculator. Nothing you can't do. It's kind of funky, but it's all stuff, like I said, you can totally conquer. If you do this, all right, for Q, I had the 1 over 0.015 to the 3rd power. I had 2.9 times 10 to the 5th. So E naught, 1.00 minus 0.0257 divided by 2, natural log of Q, 0.84 volts. So having these species at less than 1 mole per liter cut down our cell potential quite a bit. We went from 1 volt down to 0.84 volts, which is a pretty good change. So Nernst equation is super important. The human body is about 37 Celsius, which is much warmer than 25 Celsius. A lot of times people studying redox reactions on human systems will have to use Nernst equation, and this is just a utility of it. But you can also do it for other concentrations of things, lots of things. It's kind of a tedious equation, but it's not hard. Just plug and chug. In this reaction, we're going to see how delta G, E naught, and K, equilibrium constants, all come together. And we're going to find delta G naught and the equilibrium constant for this redox reaction. Now, we know this is redox because copper is going to copper 2 plus, copper is losing electrons, and silver plus is going to silver. So silver is gaining electrons. So what we're going to do on this problem is we're first going to balance this thing for the E cell value, and we'll figure out the value of E. And from there, you can see we can turn an E into delta G and a delta G into K. There's all kinds of things we can do from them. So again, we're going to first find that E naught value. We're going to balance this thing out. We're going to make sure the electrons cancel. And from then, we can find delta G and then K. One thing to make sure is that R and delta G have to have the same kind of units. And remember that R is 8.3145 joules per mole Kelvin, and delta G is often in kilojoules per mole. So just be careful of that. That's the only kind of tricky thing about these. First part, just like we've done before, we're going to find the 2 balanced half reactions. The copper going to copper 2 plus 2 electrons, that's an oxidation, so you won't see that in the table, but you will see copper 2 plus and 2 electrons going to copper, which is positive 0.337. However, I've flipped it, so that's why it has a negative sign right there, and you're good to go. We need to multiply the second reaction by 2 to make the electrons cancel. Silver plus going to silver is in the table. It's positive 0.779 volts. So when you either add these two together or you do cathode minus anode, if that's your thing, you get 0.462 volts. All right, E cell is positive. And an E cell of positive means that the reaction is product favored. Something's going to happen when you activate this battery, if you will. Now, you can turn this into delta G pretty easy, and the equation to use, delta G equals negative NFE. Now, don't forget the negative sign first of all. N is the moles of electrons. So just like we saw in the last problem, the Nernst equation problem, we want to figure out the moles of electrons transferred. And if you go back to the half reactions, copper is giving up 2 electrons and the silvers are taking 2 electrons. So 2 is the operative word, the common denominator that cancels the electrons out in the half reactions. 2 electrons are being transferred. F, I said briefly, is the Faraday constant. It's 96,485 coulombs per mole of electrons. And that's what the Faraday is. It's just a number. It's a real helpful number. We'll see, but that's what it is. And then the cell potential is this number, 0.462 volts. So we calculated that from the cell potentials to get this number. And delta G equals minus NFE. And if you throw this into your calculator, this is the number you get, a big negative number. A lot of times people will divide by 1,000, which is what that part is for right there. And so then to 3 sig figs, 0.462, you would have negative 89.2 kilojoules. Notice how a negative delta G, which means spontaneous, corresponds with a positive E, a reaction that will occur. And that kind of makes sense. E's that are product favored should have spontaneous delta G's, which would be negative numbers. Okay, the last thing to do is we need to figure out what the equilibrium constant is. And I personally like delta G equals minus RT natural log of K. Now, because R is 8.3145 joules, I'm going to use negative 89,200 joules. You want to make sure they're the same kind of units. Don't put negative 89.2 in there because that would be kilojoules, all right? That's bad news. But anyway, delta G equals minus RT natural log of K. Make sure you use Kelvin temperatures. You're going to have natural log of K equals some kind of positive number. And like we saw earlier, if you take the anti-natural log, the little e to the button, e to the power of, e times natural log of something cancel, and we'll do that to both sides. So e to that big number gives an even bigger number, and that's the value of K. That's the equilibrium constant. So 4.31 times 10 to the 15th. If you keep using all the sig figs through, which is fine, it's more like 4.23 times 10 to the 15th. Anti-natural logs will really make these numbers go plus or minus quite a bit, so a little flexibility is really handy. But again, the important part here, if delta G is negative, that's spontaneous, a reaction that's going to occur. And a negative delta G should correspond to a product favored K, a value of K that's greater than 1. So all of these things are going together. So notice that positive E values correspond to negative delta G's, and both of those corresponds to K's greater than 1. You can do the same thing in the opposite direction. A negative E cell value would correspond to a positive delta G, non-spontaneous, and a positive delta G would correspond to a K number which is less than 1, which is reactant favored. All these things kind of come in together. In this question, we want to turn silver ion, silver plus, into silver metal, metallic silver, which is a solid, all of its electrons and protons. And what we're going to do is we're going to basically shoot electricity through it. And electricity is used, and there's like intensities, if you will, of electricity. It's measured in amperes, that capital A right there. So we're using a current, an electricity of 1.12 amperes for 2.40 hours. And the question is, knowing all of this, what mass of silver will form? So notice here that we're trying to find how many grams of the solid will appear. And this problem at first might seem a little weird, but it's actually pretty chill. And it's kind of a cool kind of a problem to do, and there, you'll see what's happening. Some things to get started here. All right, charge is measured in coulombs. So the more positive charge you have means the more coulombs you're going to transfer. You can also have negative coulombs and stuff like that, but in this case, positive. That amp, which is how the current is measured, an amp is nothing more than a coulomb per second. So if you have a current of 1.12 amps, that means you have 1.12 coulombs going by per second. So what I would do in a problem like this is automatically just turn amps into coulombs per second. Amp isn't very helpful really for chemists, as you can see here, but coulombs are. So 2.40 hours, that's a time, and we can turn that time in hours into a time in seconds. And if you do that, then you'll end up with so many coulombs of charge that are being placed inside the silver ions to make silver metal. So if you look at this, that's what this part is right here. 1.12 amps is 1.12 coulombs per second. And if you turn the hours into seconds, and again, there's 60 minutes per hour and 60 seconds per minute, all of those things cancel out except for the coulombs. And again, remember, the amp is a coulomb per second. So all the time is gone and you're left with just coulombs. That's cool. That's the amount of charge that has been transferred to the silver plus in that 2.40 hours. However, it doesn't really help us with the silver right now until we go back to the Faraday constant, that 96,485. And the Faraday, the F, 96,485 coulombs per mole of electrons. So every time you have a mole of electrons, you have transferred 96,485 coulombs. So notice how we start with coulombs. We'll divide by the Faraday to make the coulombs cancel. We're going to have then so many moles of electrons. So in that 2.40 hours, we transferred 0.100 moles of electrons to the solution. Okay, that's interesting, but how do we go from moles of electrons to grams of silver, Russell? And I totally understand. This problem has silver plus going to silver. So 1 electron is needed per 1 silver ion to make 1 silver metal. So what that means is 0.100 moles of electrons can be added to 0.100 moles of silver plus to make 0.100 moles of metallic silver. So we're going to transfer moles of electrons into how many moles of silver can be made, and then use molar mass to go to grams. So this last step right here, because silver is silver plus, it's like silver plus electrons going to silver. All right, that's kind of the reaction that's happening. 1 silver plus per 1 silver. Oh, that looks like a Y. It feels weird to write on these things. Sorry. Anyway, so 1 mole of electrons is going to convert 1 mole of silver. That's what it comes down to. You can also use the charge on the ion to figure out that ratio, which is pretty cool. But anyway, once you have moles of silver multiplied by the molar mass of silver, 107.9 to 3 sig figs, 10.8 grams of silver have been made. And that's all there is to it. So let's review here what happened. Amps, if you see them, are no more than coulombs per second. And you can convert time into seconds and then multiply by the amps to figure out how many coulombs. The Faraday constant allows you to go from coulombs to moles of electrons. And then the ion itself will determine how many moles of electrons are needed to make 1 mole of the solid. And then you can use molar mass. These problems either go from time to mass. This problem went from 2.40 hours into mass in grams. Sometimes these problems go from mass back to time. Like it'll say, well, 10.8 grams of silver, how long will it take? Like 2.40 hours. These problems go one or the other ways, and they're not too hard. I find them kind of fun, but again, I need to get outside more probably. One thing that's going to help you here is that every time you see an amp, that capital A, that that means coulombs per second. So what that means is you're getting 0.66 coulombs per second that you use this amount of electricity. But you need to know, of course, then how many moles of electrons you need. That's where we can use these formulas. So in this problem, we have copper 2 plus going to copper metal. So this is a 2 electron transfer. It takes 2 electrons to turn the copper 2 plus and copper 2 sulfate into copper. So if we have 0.50 grams of copper that we're after, you can turn grams of copper into moles of copper. 63.55 is the 4 sig fig value for copper on the periodic table. And then every one of these coppers is going to need 2 moles of electrons because, again, we're starting with copper 2 sulfate, copper plus 2. 2 moles of electrons will make that copper 2 plus into copper. So that means we need positive 0.016 moles of electrons. If you remember that the Faraday constant is 96,485 coulombs per mole of electrons, and we need 0.016 moles of electrons, that means 1.5 times 10 to the third coulombs is the charge we're going to need. And again, that seems like a big number, but it doesn't really mean much. So this is where that amp value finally is going to pop in. So the amp is equal to a coulomb per second. That means that the electricity is delivering 0.66 coulombs per second. And if this number, 1.5 times 10 to the third, is the number of coulombs we need, we can then take the coulombs, divide by the coulombs per second in order to get just seconds. And this comes out to be 2,300 seconds. And if you divide that by 60 seconds per minute, it comes out to be about 38 minutes. So it should take about 38 minutes if we apply 0.66 amps to get 0.50 grams of copper out. And this is the kind of thing you can do with electrolysis. So along the way, remember that an amp is equal to a coulomb per second. The Faraday constant will be important. 96,485 coulombs are given in a mole of electrons. And we'll need the type of metal to figure out how many electrons we need. So this is copper 2 plus going to copper. It's a 2 mole of electron per mole of copper transformation. All stuff you can do, follow the units, good to go. Okay, so that's it for problem set number 5. I appreciate you spending your time with me here, and I hope this has been useful. I do encourage you to check out the study guide and concept guide for this chapter, which are available in the companion and also online. You can also look at the types of equilibrium constants. Good luck with your studying, and have a wonderful day.